Flight of the Space Shuttle Challenger on Mission 51L, the 25th flight of the Space Shuttle program, began at 11:38 a.m. Eastern Standard Time on January 28, 1986. It ended 73 seconds later in a structural breakup of the external tank and orbiter, in which the 7 crew members perished. The solid rocket boosters continued in flight and were destroyed by the range safety officer 110 seconds after launch. The delivery and assembly of 51L launch vehicle components began months prior to launch. The solid rocket booster segments were transported by rail to the Kennedy Space Center. The SRBs were inspected and partially assembled at the rotation, processing, and storage facility. The segments were then moved to the Vehicle Assembly Building, or VAB, where they were stacked on the mobile launch platform. The external tank arrived at KSC by barge and was moved into the VAB, where it was checked out and mated to the stacked solid rocket boosters. After orbiter checkout, Challenger was rolled into the VAB and mated with the assembled external tank and SRBs. The STS-51L vehicle was transported from the VAB to the launch pad on December 22, 1985. At a crawler speed of approximately 1 mile per hour, the journey takes about 6 hours. The launch was rescheduled several times, resulting in the final countdown on January 28, 1986. The weather was forecast to be clear and cold, with temperatures dropping into the low 20s overnight. The fueling of the external tank began at 1:25 a.m. Ice had accumulated on the launch pad during the night. Several water systems were opened slightly and allowed to flow into drains. The drains froze and caused overflows. High wind gusts spread the water over large areas and ice formed. The air temperature at launch was 36 degrees Fahrenheit. This was 15 degrees colder than any previous launch. At T-minus 7 minutes and 30 seconds, the ground launch sequencer began retracting the crew access arm. The arm can be put back in place within 15 to 20 seconds if an emergency arises and the crew must evacuate the pad. At T-minus 3 minutes and 15 seconds, gimbal checks of the orbiter main engines were performed. All 3 engines move in a pre-programmed pattern to verify ascent flight control. The gimbal sequence ends with the engines in their start positions. At T-minus 2 minutes and 55 seconds, external tank liquid oxygen pressurization began and main engine purging was completed. At T-minus 2 minutes and 50 seconds, retraction of the gaseous oxygen vent hood began. The ground launch sequencer verified its full retraction at T-minus 37 seconds. Sound suppression water was started at T-minus 16 seconds. At T-minus 8 seconds, hydrogen igniters were turned on to burn off any free hydrogen. 6.6 seconds before launch, Challenger's liquid-fueled main engines were ignited in sequence and run up to full thrust. Thrust from the main engines bends the shuttle stack. When it returned to vertical, the solid rocket boosters ignited. At T0, the hold-down bolts were explosively released. After the initial pre-release twang motion, structural forces on the assembly are dissipated through vibration at a rate of 3 cycles per second during the first few seconds of flight.
Space shuttle mission, and it has cleared the tower.
Roll maneuver was initiated at 7.724 seconds. The maneuver was completed at 21.124 seconds.
Normal throttles for most of the flight, 104%. We'll throttle down to 65%.
The main engines were throttled back to 65% at 35.379 seconds for about 16 seconds in order to alleviate loads during maximum dynamic pressure.
Velocity 2,257 feet per second. Altitude 4.3 nautical miles. Downrange distance 3.
The engines were then throttled up to 104% at 51.919 seconds.
Up 3 engines now to 104%.
Challenger, go at throttle up.
During the flight, telemetry data gave no indication of problems.
1 minute 15 seconds. Velocity 2,900 feet per second. Altitude 9 nautical miles. Downrange distance 7 nautical miles.
The solid rocket boosters continued in flight and were destroyed by the range safety officer 110 seconds after launch. Data from nearly 200 cameras were analyzed during the investigation. The following sequence of events is based on the evaluation of film, video, and telemetry data. This graphic indicates viewing angles for 3 cameras in the vicinity of the launch site. The first view shown is from camera E63 at the lower right of the chart. At 0.678 seconds into the flight, a strong puff of gray smoke can be seen spurting from the vicinity of the aft field joint on the right solid rocket booster. The vaporized material streaming from the joint indicates there was not complete sealing action within the joint. This second view is from camera E60. The smoke can be seen between the right SRB and the external tank and initially moves in the upward direction. The angle between this view and E63 is approximately 100 degrees. With E60 and E63 side by side, it is clear that when smoke is first visible to camera E60, it is not yet visible to E63. 0.2 seconds later, it becomes visible to E63 and is seen in multiple lobes, or puffs, reaching maximum visibility at about 1.9 seconds. A third, higher resolution camera, D67, was located east of the launch pad. D67 recorded this view of the smoke at approximately the same time of maximum development. Smoke appears to the right side of the SRB only, while normal water condensation vapors appear to the left. This plan shows that none of the cameras directly view the surface of the right SRB in the shaded region of the graphic. Analysis of film from several pad cameras indicated that the smoke came from between 270 and 310 degrees on the circumference of the aft field joint. As indicated on these pre-flight photos, the smoke emerged from just above the strut between the SRB and ET at a point along the longitudinal axis near the aft field joint. The multiple smoke puffs occurred at a rate of about 4 times per second, approximating the frequency of the structural load dynamics and resultant joint flexing. This greatly exaggerated computer animation depicts the flexing of the SRB joint. This flexing increased the gap between the tang and clevis at the location of 2 rubber O-ring seals. Last evidence of smoke above the aft attach ring appears at 2.733 seconds. The last indication of smoke dispersing below the aft dome appears at 3.375 seconds. Film records of the assembly of the solid rocket booster were reviewed to determine any evidence of cause for the smoke. Photographs taken just prior to mating of the booster segments at the aft field joint show the O-rings installed in the grease clevis grooves. A subtle variation was detected, but through computer enhancement was determined to be a shadow caused by irregularities in the grease. No evidence of O-ring defects was observed in any of the stacking photography. The facility gaseous hydrogen vent arm was not captured after retraction at launch. Film analysis, however, showed that it did not rebound and contact the vehicle or contribute to the accident. Post-launch inspection of the hold-down posts revealed that the kickspring assemblies on 4 of the posts were missing. Detailed analysis determined that the assemblies could not have become detached prior to T plus 850 milliseconds and were not a contributing factor to the smoke observed at liftoff. The next significant event was the development of the SRB burn-through plume. Camera E207, located about 6 miles north of the launch pad, shows the growth of this plume. The first evidence of flame appeared on the right solid rocket booster at 58.788 seconds. This occurred as the main engines had been throttled up to 104% thrust and the SRBs were increasing thrust. Camera E203 was located west of the launch site and gives an aft view. The exposure was set for the booster nozzle plumes. This graphic illustrates the location of the flare. The flare was located near the aft field joint, approximately 300 degrees circumferentially, which is consistent with the location of the smoke emissions at liftoff. Within half a second, the flame had grown into a continuous and well-defined plume. At about the same time, telemetry showed a divergence in chamber pressures between the right and left SRBs. Pressure in the right SRB chamber was lower as a result of the growing leak. The plume is seen here impinging directly onto the surface of the external tank and the lower aft strut at 60.248 seconds. At about 62 seconds, the control system elements began to respond to the forces caused by the plume. As recorded on E207 and E204, the first visual indication that the anomalous plume penetrated the external tank was seen at 64.66 seconds as an abrupt change in the shape and color of the plume. This is an indication of hydrogen leaking from the external tank. At 64.705 seconds, a bright sustained glow developed between the orbiter and the external tank. Slight changes in the hydrogen tank pressure telemetry data confirmed the leak 2.2 seconds later at 66.8 seconds, when the LH2 tank pressurization system could no longer maintain its normal repressurization rate. At 72.6 seconds, the LH2 tank pressure could no longer be maintained, indicating that the leak path had significantly increased and was growing rapidly. At 72.2 seconds, the guidance system showed that right SRB motion diverged from the orbiter and left SRB, indicating that the lower ET SRB strut was severed or pulled loose. During this time frame, exaggerated steering commands and control system responses registered in telemetry data. At approximately 73 seconds, both liquid hydrogen and liquid oxygen pressure to the main engines showed a significant drop. This was followed at 73.124 seconds by the appearance of a circumferential white pattern around the ET aft region, suggesting LH2 tank structural failure. 13 milliseconds later, at 73.137 seconds, vapor was observed at the inner tank, indicative of the liquid oxygen tank failing. This can be attributed to abnormal loads induced by either the right SRB rotation at the forward attach point or the propulsive forces created by the LH2 tank aft bulkhead failure, probably both. Within milliseconds, liquid oxygen was observed streaming along the external tank. At 73.191 seconds, a flash was observed between the ET and orbiter that was immediately followed by the start of total vehicle breakup at 73.213 seconds. During the next 100 milliseconds, additional flashes occur in the SRB forward attach area. As the ET broke up, the released fluids vaporized rapidly, producing an expanding cloud of gases, vapors, and cryogenic fluid with embedded debris and localized combustion of mixed gases. No shock wave or other evidence of a violent explosion was detected in the imagery. Illumination from a combination of SRB plume radiance, reflected sunlight, and peripheral burning of gases gives the cloud the appearance of a fireball. By 73.6 seconds, the main engines were in automatic shutdown mode as a result of reduced propellant pressures. The last telemetry from Challenger was received 73.618 seconds after launch. The actual vehicle breakup was essentially obscured from view by the vapor cloud which abruptly enveloped the vehicle. Hundreds of fragments were noted exiting the ET cloud. Those identified included the shuttle main engines, the left wing, crew cabin, and both SRBs. Approximately 1 second after initial breakup, film showed the front segment of the orbiter emerging from the cloud. The nose, crew cabin, and a portion of the cargo bay make up the orbiter in this view. Nitrogen tetroxide oxidizer from the forward reaction control system provided a distinctive orange-brown color to the cloud. By 74.578 seconds, a yellow cloud or flash was visible near the orbiter nose segment. This is believed to be caused by burning monomethyl hydrazine from the forward RCS. The flash reaction from the RCS propellants abated, revealing separation of the nose section from the crew cabin. Less than a quarter of a second later, the crew cabin was noted to be severed from the cargo bay. Igniting of propellant discharge continued to be observed from the forward RCS. A camera south of the launch pad recorded a wider array of debris exiting the vapor cloud. The initial emergence of the crew cabin from this perspective was at 75.237 seconds. The initial path of the crew cabin from the vapor cloud carried it across the path of an adjacent contrail, clearly revealing its truncated form and attitude. The left wing became visible at 78.531 seconds. The main engines and crew cabin are also identifiable. After 10 seconds, the crew cabin was seen again with the front end and top of the cabin visible. As the subject moved further away and dropped lower on the horizon, the quality of the image for visual analysis deteriorated rapidly. Long-range tracking cameras followed the SRBs through range safety destruct. At approximately 75.8 seconds, the right SRB was seen exiting the cloud. Camera E207 shows the right SRB after the breakup, and the joints are clearly visible except for the aft field joint. This confirmed the location of the plume along the longitudinal axis of the SRB. The separated nose cap and deployed drogue parachute are identified at approximately 76.4 seconds. The shock wave from the detonation of the linear-shaped charge on the right SRB can be seen clearly. Simultaneously, the left SRB was destroyed. At approximately 37 seconds, Challenger had encountered the first of several expected high-altitude wind shear conditions, which lasted until about 64 seconds. These wind shears are best illustrated by the effect on the booster exhaust trails. The effect of wind shear was immediately sensed and countered by the guidance, navigation, and control system. Wind reconstructions were aided by comparing predicted exhaust trail shapes with acquired photography. The reconstructed winds were used in trajectory and flight loads analyses, which verified that the loads were within limits. Several flashes in the SSME plumes were observed during the flight. As similar flashes have been seen on several previous flights, they are considered not to have contributed to the accident. The visible condensation that appears in this frame is created by shock waves which develop as the vehicle passes through the speed of sound. A large-scale search effort was initiated to recover the space shuttle debris. 22 ships, 6 underwater search vessels, and 33 aircraft participated in the operation. The pieces recovered initially were those found floating on the surface. The submarine fleet was used to locate and inspect underwater debris. Objects identified as being important to the investigation were retrieved. "50% of the entire vehicle was recovered in the effort. The ocean search area was located at the edge of the Gulf Stream at depths up to 1,200 feet. Approximately 93,000 square miles of ocean were searched. The recovered hardware was brought to the logistics facility, where reconstruction efforts helped to verify the investigation team's findings, as well as to analyze the structural breakup mechanics of the orbiter, ET, and SRBs. Inside the logistics facility, parts were arranged on the floor according to their location on the vehicle. "45% of the orbiter itself was recovered. The debris confirmed that the orbiter and its payloads did not contribute to the cause of the accident and that the orbiter breakup was a result of aerodynamic effects rather than explosive effects. Shown here are parts of the orbiter forward fuselage structure, which surrounds the crew cabin. Extensive heating and erosion was detected on the right aft section of the orbiter. The paint was scorched and blackened on the right side of the aft fuselage. Thermal distress was apparent on the right rudder speed brake, while the left showed little effect. Thermal effects were also seen on the elevon. The aft left side of the orbiter showed no apparent sign of heat damage. The remaining recovered parts of the orbiter showed no evidence of fire or explosion from within the vehicle. All 3 main engines were recovered and helped to verify that they did not contribute to the cause of the accident. The external tank was similarly reconstructed. 25% of the liquid hydrogen tank, 80% of the inner tank, and 5% of the liquid oxygen tank was recovered. Most of the external hardware was also recovered. The nose cap sustained very little damage. In general, the recovered pieces were quite large. The spray-on foam insulation exhibited varying degrees of thermal effects from extreme charring to practically no effect. The external tank range safety destruct explosive charges housed in this cable tray were recovered undetonated, eliminating them as a possible factor in external tank breakup. The intertank region showed signs of buckling in the fore and aft direction. This would be consistent with the impulsive thrust that resulted from the sudden loss of liquid hydrogen from the aft section of the tank. This shearing failure of the forward attachment fitting with the right SRB was caused by the booster's rotation after the aft strut area failed. The stiffener stringers on the right-hand side of the intertank show evidence of contact which match marks on the forward assembly of the right SRB. A section of the ring frame and a section of the aft dome from the lower strut attachment area was recovered in one piece. The lower strut attachment fitting had been pulled away. The effects of the anomalous SRB plume can be seen on the external tank, excluding an area which was shielded by the strut and attachment fitting. Approximately 50% of solid rocket booster hardware was recovered. An ordnance storage facility was used to house the motor case pieces, as some contained unburned propellant. Marks seen on the right SRB frustrum match the contact area shown previously on the ET intertank stringers. The size and location of the burn-through as indicated by the recovered SRB debris were illustrated on an assembled booster. The aft center section of the joint shows a large hole centered at the 307-degree circumferential position. The irregular hole is roughly rectangular and is about 27 by 15 inches. The steel case material showed evidence of hot gas erosion caused by combustion products flowing through the opening. The aft section of the right SRB showed a hole approximately 33 by 21 inches. The burn surface extended into the aft attached strut region. The exterior surface of the aft case featured a large heat-affected area. The shape and location of this heat spot indicates an impingement from the escaping gases. There was a small burn-through in the case wall which appeared to have penetrated from the outside in. This was due to the impingement of hot gases from the anomalous plume. The hole in the solid rocket booster segments was the result of the joint leakage on the right-hand SRB, which was determined to be the cause of the accident. The Presidential Commission concluded that the cause of the Challenger accident was the failure of the pressure seal in the aft field joint of the right solid rocket motor. The failure was due to a faulty design, rendering the seal unacceptably sensitive to a number of factors. Those factors include the effects of temperature, physical dimensions, the character of materials, the effects of reuse and processing, and the reaction of the joint to dynamic loading. More detailed analyses are contained in Volume 3 of the report of the Presidential Commission on the Space Shuttle Challenger accident.